Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is power quality applications, measurements, and analysis. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. Oh, and we might have pause. There we go.
Sorry, little
We're
difficulty.
good. Yeah. Beautiful. So that control panel right there, you can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and a link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenters today are Andrew Sagel, Product Manager, and Sanket Bolar, Applications Engineer. Also, to assist with today's Q&A session, we will have joining us Dinesh Chajer, Technical Support Group Manager. All right, let's go ahead and get started. Thank you so much for joining us today, Andrew.
Thank you, and good morning, everyone, or good afternoon, actually. And what I'd first like to throw out there is just a general question. What is power quality? There's many different answers you can get, but the actual technical definition is it's the concept of powering and grounding sensitive equipment in a manner that's suitable to the operation of that equipment. So basically that means if you have everything working as it needs to be working, you don't have a power quality problem. If you have equipment that is having problems and is due to the incoming power, you do have a power quality problem. Now, this presentation, what we're going to do is we're going to cover the general PQ phenomenon and their effects and their causes, so how they affect equipment and what causes these phenomenon. And in some future presentations, we'll cover specific PQ issues such as equipment going offline, equipment and breakers tripping, how to troubleshoot those issues, troubleshooting lighting issues and motors and more. So stay tuned for future presentations that will dive into more depth on particular topics. So in this presentation, what we're going to do is we're going to cover several phenomena, including undervoltages, overvoltages, dips and swells, transients, unbalance, flicker, RVC, also known as rapid voltage change, harmonics. Then we're also going to look at how to properly conduct a power quality investigation, and then how are we going to do a data analysis. So, undervoltages. And undervoltage is a decrease in the RMS voltage that is less than 0.9 percentile units, or 90% of the nominal, for a duration that is longer than 1 minute. So what does this do? Well, when we get undervoltages, the most common effect it's going to have is it is going to cause heating effects in motors. Motors that require a constant energy, a constant power output. As the voltage drops, they have to increase the amount of current they're drawing. The increased current will increase the heating in the coils. So undervoltages can be detrimental to motors. In lighting systems, you can see things like incandescent lights. Obviously, we know they dim when that happens. Fluorescent lights, you may see them actually start to flash, or they could turn off completely and may not turn on. And of course, any manufacturing equipment could end up dropping offline. Now, undervoltages are typically not due to system faults. Most of the time, 90% of the time, they are load side issues. And they have to do with large loads coming on, cap banks possibly turning off, or overloaded circuits. Typically, the utilities try to maintain about a plus or minus 5% voltage regulation. But you can have them you can have these caused on the utility side by overloaded feeders, incorrect tap settings, malfunctioning regulators, trying to get that out, blown fuses and cap banks, or even capacitor banks that are in service during light load conditions. These are things that can cause it from the source side. But as I said, typically this is a load side issue. Now, overvoltages are just the opposite. We're going to be seeing those are an increase in the AC voltage greater than 1.1 percentile units, or 110% of nominal, that occur for a duration of over 1 minute. The biggest issue you're going to run into with overvoltages is that repeated overvoltages will cause stressing and damaging of equipment insulation. They can also, over time, as that insulation wears out, they can cause damage to transformers and motors. If it's large enough, you can get a flashover in certain areas, and of course, you can get tripping breakers and equipment to trip offline. So in any of these cases, we do want to look at overvoltages. And also in motors, when we go to turn the motor on, we have a current inrush. If the voltage is sitting too high, you can get excessive current on that inrush as well. So, what are our common causes of overvoltages? Well, again, these are typically load side issues that have to do with large loads turning off. You can also have issues with solar panels. When solar panels are put onto the system, if you don't have good voltage regulation, you can end up having overvoltage conditions on that system. And again, other potential overvoltage causes can include incorrect tap settings on transformers, resonance, and also in delta systems you can get this, because if you have a sag or a fault on one leg of the delta, what will happen is the other two will rise up. So you can end up with overvoltages there. And also with long cable runs, what you may find, if you have long cable runs with light loads at the end, you may look at that end voltage and find it's sitting up higher. You have an overvoltage condition there, and that is due to the fact you have such a light load there, and those long cable runs will have capacitance to earth, which will hold that voltage up at the end. So you'll end up seeing more of a peak than an RMS value there. Voltage dips and sags. Now, the term dip and sag, they basically mean the same thing. It all depends on what portion of the world you're in. In the US, we tend to look at them as sags. In other parts of the world, they are referred to as dips. They mean exactly the same thing. Now, when we look at a short duration, the voltage dip or sag is a short duration event. It's always between half a cycle and a minute. Okay, that's what makes them different than overvoltage or undervoltage events, is that the dips, swells, they're short duration, under a minute. And basically an RMS dip, voltage dip, is between 0.1 and 0.9 percentile units, or 10% and 90% of nominal. And there's three categories, and they're all based upon the duration. And this really has to do more with protective device responses when you hear these terms. Instantaneous means that the sag duration was between half a cycle and 30 cycles. Momentary, 30 cycles and 3 seconds. Temporary, 3 seconds and 1 minute. An interruption is literally when the RMS voltage drops to less than 0.1 percentile units, or under 10% of nominal. And this is literally a loss of power. And that interruption will be under a minute. It will be a half cycle to a minute. And these are broken up into two categories, momentary and temporary. Momentary being half a cycle to 3 seconds. Temporary, 3 seconds to 1 minute. Now, what are the effects that these dips can have? Well, one of the biggest effects you're going to see is equipment shutting off. When you get a large enough dip that occurs, keep in mind is that a lot of equipment is run by power supplies. A power supply takes the AC voltage in, converts it to DC, and it does that at the peak of the wave. It then has a capacitor or capacitors that hold that up until the next peak comes. If your dip occurs and it has sufficient magnitude and duration that that capacitor starts to discharge, then the power, the voltage that's supplying the equipment will dip down and can trip offline. Okay, so this is how it can cause equipment to trip off. It can also cause changes in speed of equipment, and of course, dimming of lights. We see that all the time with incandescent lights, especially, are susceptible to this. So what causes them? Again, these are typically always load side events, and they're typically due to large equipment turning on. You're getting high currents that are inrushing in. And as these currents increase, what happens to the voltage? It's going to dip down momentarily. When you have a large motor that turns on, like an induction motor, these will draw 6 to 10 times their full load at startup. So you'll get a significant inrush current that comes in, and that will cause a voltage dip. And of course, other things that can do this is anything that really changes that system impedance. Intermittent connections will do that, and also source side faults, a single line to ground fault or a line to line ground fault. You will see that dip, and that will be there until the protective equipment trips off. And the big thing is when you see those dips occurring, if they're load side and you have an inrush occurring, you'll see current going up where the voltage is going down. When they're source side, for the most part, when the voltage goes down, you'll see the current go down most of the time. If you have a motor load, you could see the current go up, but for the most part, that's a good methodology to help determine if it's source or load side, but you do need to know what your load is. Voltage swells, these are increases of voltage of 1.1 percentile units or 110% for a duration of half a cycle to a minute. And again, these are broken down into instantaneous, momentary, and temporary. And again, these can cause problems with equipment tripping offline, tripping breakers, relay switching, and of course, lighting problems. You'll see the lights swelling, the light out of the light. And repeated swells will also have impacts on your insulation as well that can affect transformers, cables, switch gears, things of that nature. So what causes voltage swells? Again, these are pretty much load changes, switching off of large loads, switching on to cap banks, and again, the source side faults. And again, these are much less common than sags. Sags are the most common problem we'll see in power quality. Swells are rarer than them. But again, a signal line to ground fault on a delta, keep in mind, when that one line goes down, when the one phase goes down, the other phases go up. So this will create a swell until the protection equipment kicks in. Now, let's go into other things such as transients. Now, the difference of transient is a very short duration event, okay? And there's basically two different types. They're typically sub-cycle events. They're going to be less than a cycle. And there's basically two different types. We have the oscillatory transient, which we see on the upper image here. And it's categorized by this ringing out that you see there. These are low frequency transients, typically a few hundred hertz in region. And they are typically due to capacitor banks switching in. And then you also have impulse transients. Okay, these impulse transients are high frequency transients that are a few hundred kilohertz regions. These will typically be in a unidirectional direction, or they don't have that ringing out, I really should say, and they can be very short in duration. So what do transients do? Why are they bad? Well, number one, transients can damage insulation because insulation has a capacitive property to it. Both cables and capacitors have this capacitive property. So right here, what I'm looking at here is on the left, you see a capacitor. You have two conductors separated by an insulator. Now, here's my cable. I have a conductor surrounded by an insulator with another conductor. It's the same thing. So what happens to a capacitor when I put a changed voltage on there? I'm going to get a voltage difference potential across it. I'll get a momentary current flow until it charges up. The same thing happens with a cable. When you get that difference in potential, you get a momentary current flow across that insulator until it charges. Hence, one of the first things you do when you're changing a large cable is what do? You discharge it because it holds a charge. The longer the cable, the higher the capacitance to it, the more charge it can hold. As you get transients that occur, what they're doing is they're rapidly changing the difference potential across those conductors, or across the insulator, I should say. So you get a momentary pulse that goes through, and it will over time break down the insulator. And as the insulator starts to break down, its impedance in that section where it's breaking down is getting lower. So as you hit it with more transients, what ends up happening is that same area starts conducting that electric pulse, and it will break down over time, and that's what wears down these insulations. That's why transients are so bad for it. Now, when you look at things like motors and transformers that have windings in them, you have, when transients are applied to them, what happens is that they basically will dissipate their energy over the first few coils in there. So each successive coil presents more resistance and capacitance. So as that transient is applied, its energy will dissipate in the first few coils. So typically, unless there's damage somewhere already existing in the insulation, the majority of the energy you'll see when you have transients causing damage to this will be on the first few coils within the motor or the transformer. Excuse me. The other big impact you can have with transients is in lighting, especially fluorescent lighting. Now, I don't know for any of you that have replaced these fluorescent lights, you'll notice that when they burn out, they're usually dark on the ends. But sometimes when you look at them, you'll actually see little black spots in them. These black spots are mercury deposits, and they are caused by transients hitting the lights. And over time, that reduces the output and the life of the light. In fact, in this image here, we can see where this light really got hit by a relatively high transient. You can see the mercury deposit on it. And as I said before, when capacitor banks kick on, this is what will lead to your oscillatory transient and your impulse transient. Lightning is a major contributor to this. Now, I don't mean a direct lightning strike, because a direct lightning strike is pretty obvious. Anything that's hit by lightning, you're not going to have any questions of what happened. But what happens is that when you have lightning that comes down, it creates a large magnetic field. As that magnetic field crosses electrical wires, it induces an electrical field in the wire. And you'll see that as your transient pulse. And lightning is a common cause. It's not the only one, because obviously high switching equipment can also do it on the load side. But lightning is a very common cause of impulse transients. Unbalance. This is the definition of unbalance based on your standards. And it's unbalance is a condition in a polyphase system in which the RMS values of the line voltage of the fundamental component or the phase angles between consecutive line voltages are not equal. And basically what that means is that if my three-phase magnitude is not equal, or my phase angles between them are not equal, I have some level of unbalance. The biggest issue you're going to see with unbalance comes with motors. Is that a motor really, you want to keep that the balance of the motor to within about 1%, fairly tight, because the more unbalanced it gets, more unbalanced your voltage gets, your current will typically be about 6 to 10 times higher unbalanced than that, because it's trying to compensate. So you'll get much larger current unbalances between the phases, which will cause heating in some of the phases, much higher heating than in other phases, which will lead to premature motor failures. So when you're seeing this type of thing, unbalance is a key thing to look for. Now, when we measure unbalance, there's a couple ways it can be done. There's an Ansi measurement. And when you look at motor specifications, typically their measurement is an Ansi measurement. And what they're basically doing in an Ansi measurement is they're taking the line-to-line voltages, adding them up and dividing by 3 to come up with an average. Then they compare each phase to that average, and the one that has the largest unbalance is what your unbalance is stated at. Now, this is a great approximation of unbalance. The problem is it only takes in the worst phase. It doesn't take into account the other 2. So there's another method that's also done, and this is the method that's typically referred to in power quality standards. And this is looking at some symmetrical components. And when we look at symmetrical components, what we're really looking at is what's called the positive sequence, negative sequence, and zero sequence components. And this has to do with the magnetic rotation around the magnetic field rotation around the wire. Basically, positive sequences rotate in the same direction as the fundamental, negative in the opposite direction of the fundamental. Zero sequence have no rotation. I'm going to explain this a little later in the presentation. But basically, when you look at a specification, it may say in a PQ standard that your unbalance can't exceed 2%. What they're referring to is your negative sequence factor, which is the negative sequence compared to the positive sequence times 100. And this is really the important thing to understand. That's the value to look at. Now, negative sequence unbalance will have larger impacts on motors because it's rotating in the opposite direction, so that it is also creating a counter-rotational torque. Zero sequence unbalance will produce much higher neutral currents in a system. So if you are seeing neutral currents, you want to look at your zero sequence components. If you're seeing problems with motors, it's really the negative sequence component you want to look at. And I actually already talked about this, so let's move on. Unbalance. The minor voltage unbalance, typically under 2%, and it's typically due to issues like large single-phase loads, blown fuses and cap banks, single-phase line regulators. Residential solar panels are also a culprit too, because when those get put on, we think about it, those are put on, they're not put on three-phase, they're put on 1 or 2 phases, so that they're going to create more voltage on those phases than on the other ones. So those are a big culprit of unbalance in the utility area. Larger unbalances greater than 5% are usually due to problems with open protection devices or wrong tap settings or transformer issues. Flicker. Now this is a very specific problem. This relates to human perception, and it actually was developed for incandescent lighting. Okay, the important thing to understand about flicker is this is not referring to voltage flicker. It's actually a measurement of light flicker. Okay. When we measure flicker, what we're doing is we are measuring the instantaneous voltage and then comparing it to a rolling average, and we come up with a difference there. This difference is then multiplied by a weighted curve. The weighted curve was based upon testing done on how sensitive the human eye is to lighting, the lights flickering, incandescent lights flickering at 120 volts 60 hertz and 230 volts 50 hertz. Okay. Now keep in mind that weighted curve is meant it was done on incandescent lighting only, so that becomes important. The value is then put through a statistical analysis to come up with what's called the short-term flicker, or PST. This is your flicker based on 10-minute intervals, and then that is put into another statistical analysis that comes up with your PLT, or long-term flicker, which is based on a 2-hour interval. So what does all this mean? Well, basically, if your short-term flicker is less than 1.0, you really have no issues with it. Really, any light flicker from that should not cause noticeable issues with the human eye. If it starts going over 1.0, it means that the light flicker you're seeing could have impacts on the human eye, where they could start noticing it and it could become irritating. What's important to understand about this is that this is calculated using the weighted curve that was based on incandescent lighting, so that it really only applies to incandescent lighting, that 1.0 level. You can do flicker measurements on other types of lights like fluorescence and LED, but that 1.0 level doesn't mean anything with them, because typically it's going to take a lot more flicker to affect a fluorescent light and an LED light. And then an incandescent light is much more susceptible to it. So although you can take the measurement, the actual value, it doesn't have a particular reference to it. Okay. Now, rapid voltage changes are RVC. Now, this does affect all types of lighting. Okay. Rapid voltage changes are fast rise and falls to the RMS voltage, and they're going to be typically over 3%, but under 10%. And the biggest issue it will cause is, again, you'll see changing light levels, and this will be, again, you'll see this in very clearly incandescent. You'll see it in fluorescent, and you may see it in LED depending on the design of the actual driver for the LED, because remember, LEDs work off DC, not AC. So they're going to rectify the AC voltage. So it all depends on the design of that rectifier that many times is embedded in the light itself. But the important thing is to realize it can affect all types of lighting. So if we are doing troubleshooting based on a lighting issue, RVC is something we want to record. Typically, it won't have impacts on other types of equipment because the changes just are not that severe. Now, what can cause rapid voltage change? Well, one of the things that can cause rapid voltage change is solar panels or any type of renewable energy that is based on changing parameters. Like when you look at a solar panel, its output is going to be based upon the amount of light that it's getting, the amount of solar radiation. As the solar radiation changes, the output changes. Wind, as the wind speed decreases, that can change. If you do not have proper voltage regulation, then what can end up happening is you can see RVC due to this. Other causes of RVC can be load side, such as very rapid load changes. If you have rapid load changing, high switching, again, this can cause RVC. So now let's go into harmonics. Harmonics are a sinusoidal component of the periodic wave that are multiples of that periodic wave. So my first harmonic, my first order harmonic is my fundamental. So it's 60 hertz. My first order harmonic is 60 hertz. My second order harmonic is 120 hertz. My third is 180 hertz. So they're always multiples of that fundamental. Now, way back, most of the loads we had were motors and incandescent lights. And these were called linear loads because they drew power, they drew current at the same rate as the voltage changed. Today, most of our loads are nonlinear loads. They run off DC, so they use rectifiers in them. Rectifiers for efficiency will only draw current at the peak of the waves. So if they're only drawing current at the peak of the waves, you are going to see harmonics. These are what cause harmonics. Now, typically, when you see a current harmonic, and if your system only has current harmonics, these will not mitigate through a transformer. However, when current harmonics get high enough, they will start causing dipping in the wave. So you can see it right in this image here. You see how that is flat on the top. That's referred to as flat topping of the wave. It's a third order harmonic. That occurs because the third order current or third order harmonics in the current has gotten high enough now that it's affecting the voltage. So when you start seeing voltage harmonics, now those will mitigate through a transformer and get throughout the whole system. So how do we categorize harmonics? Well, there's a couple different methods. One, you can look at odd, even, and triplet harmonics. Well, odd harmonics are obviously those with odd numbers, 1, 3, 5. And those are normal. These are what we would expect to see on a system. They are symmetrical and, like I said, normal. When you look at even harmonics, 2, 4, 6, these are not symmetrical harmonics. And they're not normal on the system. You should not have extreme high levels of these. These should be relatively small. If you see high levels of even harmonics, this is an indicator that you may have a faulty rectifier on the system. And it's not fully rectifying the waveform plus and minus. So this is why you've seen asymmetrical waveform. You also have triplets, or these are odd harmonics that are multiples of 3. These have a property that they don't cancel out. Now, different harmonics have different frequencies, and as you add up frequencies, they will tend to cancel. Triplets don't cancel. Their peaks line up, so they add together. So as you get these triplet harmonics, 3, 9, 15, what these will do is they'll add up on the neutral line and create high neutral currents. Okay, so this is one way we can categorize harmonics. Another way to categorize harmonics is by their sequence components. And again, this has to do with that magnetic rotation around the wire. Positive sequence rotate in the same way. The magnetic field rotates in the same rotational manner as the fundamental. Negative sequence are opposite. Zero sequence have no rotation. Okay, and if we look here, what you can see here is the first order harmonic, which is in blue, is the fundamental, and that's a positive sequence. The second order is a negative sequence. The third is a 0, and you see the pattern just repeats. Fourth is positive, fifth is negative, sixth is 0. And one of the key issues here again is when you're dealing with a motor or any rotational equipment, negative sequence harmonics create magnetic fields that oppose the direction of torque. So they can create issues like vibrations in motors and things. So that's an important thing to look at when troubleshooting a motor, is to make sure that your negative sequence harmonics are not excessive if you're having motor problems. It's something to look for. Now, when I say phase rotation, of course, I've been talking about the rotation of the magnetic field. And it's difficult to explain at times, but I think this sort of does a good method of explaining it. Is if you look at this circuit, this phasor diagram, you'll see I have phase A, B, and C labeled. And phase A, you see it's at 0, B is at 120, and C is at 240. If I keep going around in a counterclockwise motion, it then goes to 360, B goes to 480, C goes to 600, and these are all the same angles. I'm just going round and round. So when I look at my first order harmonic, looking down at the table, phase A is at 0, phase B is at 120, phase C is at 240. So I'm going A, B, C. It's a positive sequence. Let's look at our fifth order harmonic, where I'm going to multiply each by 5. So 0 times 5 is 0, 120 times 5 is 600, and 5 times 2 is 40 is 1200. So I'm looking at 0, 600, 1200. We go to the phasor diagram, take a look. You have 0 is phase A, 600 is phase C, 1200 is B. So I have an ACB rotation, negative sequence. If I look at my third order harmonic, 3 times 0 is 3, 3 times 120, 360, 3 times 240, 720. I have 0, 360, and 720. They're all A. I have no rotation, so it's a 0 sequence. So this is what we mean by positive sequence, negative sequence, and 0 sequence. So why are harmonics problems? Well, they create heating effects. And the main reason is they create eddy currents. And what happens is that when I have a current passing through a wire, an alternating current passing through a wire, it creates an alternating magnetic field. Now, in turn, that alternating magnetic field cuts the wire and creates circular currents within that wire, which are known as eddy currents. Those eddy currents create their own magnetic field, which is in opposition of the magnetic field of the fundamental current coming through it. So it creates a resistance to it. And what it will actually do, those eddy currents, is because they're creating a resistance to the flow, they're going to be pushing the current flowing through the wire toward the outside of the wire. So the majority of the current will flow toward the outside of the wire. This creates what's called skin effect. Now, if you're working with pure DC, you don't have any skin effect. You're using the entire cross-sectional area of the wire. As you start working with AC, you start getting eddy currents developing due to the alternating currents. And so you do have skin effect that happens. At low frequencies, it's minimal. But as we start getting higher and higher in frequency, so as you get higher frequency harmonics, your skin effect increases, which means you're using less and less cross-sectional area of the wire, which means it's going to get hotter. So when we're looking at things that are heating up, we do want to look at the higher order harmonics and see what do they look like. Okay, and one of the things we can look at is called K factor, which I'm not going to get into in this presentation. That will be more in a future presentation. But the harmonics can create issues of heating in transformers, in motors, in connections as well. These are all things to look for when you're looking at heating issues. So when we want to do a study, we want to troubleshoot something, how do we want to go about this? The very first thing to do before hooking up anything or taking any measurements is first plan and prepare. First thing we have to ask is, what are the reported symptoms? How often do these symptoms occur? Do we see any pattern with it? Are they always happening pretty much at the same time of day? That could be indicative of a piece of equipment turning on. You know, can we make any correlations? Big question is, has there been any changes made to the facility lately? Because that can be a clue as to something that's causing, something has changed, that's causing a problem. And here's the biggest one, which is probably the toughest too, is to try to receive input from all those involved, which is nearly impossible. Typically, when dealing with an issue, I mean, for me, I always find I'm talking with one individual. But it's good if you can talk to multiple individuals, because others may have noticed something the others didn't. So it's a very good thing to do to try to get information from more than one person if possible. Inspect everything. Check for safety hazards, check that everything's to code, and check for bad connections. Now, this is where a thermal imager may come in handy, because this will help find hotspots before you even have to do anything. Now, we're going to want to hook a monitor to it. Okay, so the first thing is we need to select a location. Where are you going to connect it? Well, if you're troubleshooting a piece of equipment that's tripping offline, or a particular piece of equipment is having a problem, a motor not coming up to full power, you want to try to get as close to that piece of equipment as possible so you can see what power, what voltage and current that particular equipment is seeing. The further away you get from it, the less representative it is. So we want to get as close as we can. Now, if it's a facility problem, or we're not sure what's going on, we can go to the point of common coupling, which is where the utility power comes into the facility. And that is where we would take the measurement at that point. We also want to take the environment into account, okay? You want to verify your instrument is rated for the proper temperature, moisture, and humidity levels, okay? And you want to also make sure that your transducers you're using, your current clamps, also have the proper rating, okay? The other big thing with current clamps is you want to make sure you use the proper range ones. I've seen in instances where people will use CTs that are rated at 3,000, 6,000 amps and be measuring 50 amps. The problem with that is you're getting a very poor resolution. So if you're going to be basically looking at nothing more than RMS, you might be able to get away with that. But if you're going to be looking at power or harmonics or anything like that, you're going to create too much error in your phase angle and also in just background noise that you'll get. Signal to noise ratio will be too high. So what we want to do is we want to try to get get an idea of what the current is going to be and try to get the range of the CT to sort of match that. And one of the things that will help is knowing what the crest factor is for the CTs and for the instrument itself. So, for example, if I'm going to use a 60 amp CT, okay, that's 60 amps RMS full scale. But now, if I have a crest factor of 4, that means it will measure up to 240 amps peak. So you can see that it has a lot of overhead in it that you can use, all right? Now, on the other side, if you go too small, you could end up saturating, okay? That's why it's sort of important to understand what that crest factor is for the current clamps and the current channels in the unit. Now, do we want to use a flexible or a split core CT? Well, the very first thing you got to see is what fits the location. If it doesn't fit, it ain't going to work. But if you're going to be measuring very low currents, split core would be more ideal to use. A flexible CT has its benefits. It's easy to get on, but it's much better at higher currents because they use air cores in them. Air cores have a lower permeability, so they are not as efficient at transferring the magnetic field, especially weak fields. So although you may get a good RMS reading, your phase angles and your signal-to-noise ratio may be off. So again, with low values, really go for split cores. If you're going for higher currents, then the flexibles are ideal. The other question is, does it require batteries? Flexible CTs have to be integrated, so they will require batteries in them, or they have to be powered by the instruments, okay? If they require batteries, you always want to make sure you put in fresh batteries. Are you trying to record DC? If you're going to record DC, you need a special type of CT, like this one imaged here in the top, which is a DC CT, and it's a Hall effect CT. These will commonly also require batteries in them unless they're powered by the unit. Another thing to keep in mind. Another thing is, what's the bandwidth of the CT you need? If you're going to be looking at a troubleshooting issue that could possibly be dealing with high frequency harmonics, you have to take that bandwidth into account. Because if I take a CT that has a low bandwidth and I'm trying to look at high frequencies, I'm not going to see it. Where this is going to become really pertinent is when you get into substations where you have to hook up to secondaries on PTs and CTs. You got to look at what their bandwidth is, because that will be the limiting factor typically in how high of a frequency analysis you can do. Okay. Now, we also, when we monitor, we want to make sure we're triggering for the right events. So we want to set the proper power configuration, and we want to make sure that we have the right events triggered, okay? So for example, if I'm going to be looking at a problem troubleshooting tripping breakers, I will want to set some current limits on there that are equivalent to the breaker level to see if I'm passing that current limit. If I'm seeing light variations, I want to make sure that I not only have dips and swells that I'm looking for, but I'm looking at RVC, interharmonics, and things of that nature as well. Now, conducting a PQ, monitoring, what we want to do is, another thing is verify the CT range is correct. This is a common problem I have seen many times, where someone hooks up a CT, and especially if it's a selectable range, they set the range in the CT, but not in the unit. So there's a mismatch there. Now, if your unit does not auto-recognize CTs, you've got to make sure that these are set properly. If they auto-recognize, it's really a non-issue. Okay. And another thing, always verify waveforms are being captured. Okay. You can capture event-triggered waveform. That's fairly common, and it's needed. If you have an event that occurs, a dip, a swell, a transient, RVC, you want to capture that waveform. However, you also want to capture time-triggered waveforms, periodic waveforms of normal conditions. Every time you have an event that occurs, it's a fault condition you're getting. So you're just seeing fault condition waveforms. The time-triggered waveforms are taken in non-fault conditions. So they have a lot of value to them in that they show you what, they give you a baseline reference to start with. And also it's ideal for doing a harmonic analysis on them, because that detailed harmonic analysis on a time-triggered waveform will let you know what your load is. And again, I don't have enough time to go into that in this presentation, but in future ones, we will cover more about analyzing harmonics and determining your load based upon the harmonic content of the timed waveform. So we now have our unit programmed, and we're going to connect it. Always use proper PPE. Okay, safety is number one. You want to verify the voltage leads are connected per the power configuration diagram. Okay, verify the CT ranges are set correctly and they're in the proper directions. The CTs will have an arrow on them. That arrow should point toward the load. Okay. Now, some power quality analyzers can also be powered off phase A. Some have to be plugged in. Some can be either. So always make sure if they can be either, you have it set properly. Ground the unit for safety. And if the unit is somewhere where people can see it, lock it up. If you can put a padlock on it, that's great. If you can hold it down. Otherwise, we've had many instances where people have put units out and the units have not been there when they got back because they were in plain sight. So before we start the recording, a good practice to do is to look at your KW and your phasors. You want to verify your KW is positive. If your KW is negative, it's highly likely you have a backward CT. And then also you want to make sure that your phase angles are appropriate per the connection diagram. And now on some analyzers, the analyzers will automatically check this and verify it and let you know if anything's wrong and tell you how to correct it. But if your analyzer does not automatically tell you it's connected properly, you have to make these checks. And this, before you walk away, just make sure that that analyzer is recording. I cannot tell you how many times we've had people set them up, made sure everything was right, and then left with forgetting to actually start the recording. We also want to make sure that we record for at least one complete cycle of the problem. And what I mean by that is that if someone tells me that they're having a problem with a piece of equipment that's tripping offline, now I'm going to ask them, how often does it happen? If they say it happens every day, well, I got to record for at least a day. If they tell me it happens once a week, I have to record for at least that week. If it's very intermittent, I may actually want to do a remote monitoring where I hook it up to a Wi-Fi or some type of Ethernet, and I can monitor remotely from my office and download the data. This way, I don't have to keep traveling back and forth between the location. So this is just a much easier way of actually trying to isolate or find those really intermittent problems. Now, analyzing the data. Getting the data is half the battle. Now, the other half is analyzing it. How do we know what we saw as a problem? Well, here's an example of a piece of equipment that's tripping offline. And if I'm troubleshooting a motor, I'm troubleshooting a transformer, I really want to look at that nameplate data to get my values. Now, with this, what I'm going to be doing is analyzing this first based on IEEE standards. So I'm looking at the different IEEE standards, and in this particular software, I can do an automated data analysis, which makes life really easy because this shows me right off the bat if I have any problems. And the way this is basically read is that the blue bars here indicate my frequency, voltage, THD, flicker, unbalance, and harmonics for 95% of the time. And as long as they're underneath the line, it's good. So that's fine. My red bars indicate what they were for 100% of the time. And you can see that on the flicker, that goes above the bar, but basically what that means is, you know, less than 5% of the time I had a flicker issue. And that's not going to cause equipment to trip offline. Okay. So then what I can do is, well, going back to this real quick, this actually tells me now that it doesn't appear to be a steady state problem that's causing it. If it were, if I had voltage out, I would go look at that. If I had THD that was too high, I would go look at that. But this is showing me that the steady states look fine. So I'm now going to look at my events that occurred. And since this has a controller to it, I'm going to use a Subima analysis. And basically what I'm going to do here when I look at this is this chart plots all my events. And I have 3 sections in here. Okay, I have the no interruption in function. So any events that are within this area are okay. They shouldn't cause a problem. I then have this prohibited region. This region here, if I have an event that occurs here, not only could it trip a piece of equipment offline, but it could damage that equipment. Then I have this no damage region, which means an event that occurs here could trip the equipment off, but it shouldn't damage it. And you can see I have multiple events that occur here. So one of my next questions is going to be, is it coming from the source of the load? So I'm going to go look at the voltage versus the current. And here, what I'm going to see is that now this, in a normal condition here, non-faulted condition, I can see that I'm getting a voltage sag that occurs, well, not really a sag, the voltage goes down a little as the current goes up. This would indicate this is a load turning on, pulling the voltage down slightly, but this isn't what caused my trip. If I go to look at where the trip occurred, I can see that it's a voltage dip that I'm seeing right there, but I really don't see any significant change in the current. This would be indicative that the problem's coming from the source side, it's upstream. So then what I want to do is take a look, is this a polyphase event or a single phase event? And when I zoom in, it's interesting, the 2 events that really I'm seeing here, one is multiple phase and the other is a single phase. So it looks like I'm seeing a couple different things happening here. And when I go look at the waveforms associated with them, I can really see that much more clearly. And basically what the problem is there's equipment coming on upstream of this that's creating voltage dips that is affecting this equipment. So this equipment needed to be isolated from it. And again, this is a relatively brief discussion of the phenomena, general overview. And in future discussions, we'll be getting into things in much more detail. And basically, I'd like to thank you for attending this portion of the presentation.
Yeah, excellent. I'm going to send this over to Sanket real quick for his portion. Are you ready, Sanket? Oh, we may have some audio issues with Sanket.
No, I was on mute, sorry. Yeah, I'm ready. Go ahead.
Really easy audio issue to solve then. All right.
Okay, so let's get started with this section of the presentation. So Andy covered the power quality bit, and he went through all these topics. Now here we are basically going to talk about the MPQ2000, and for those of you who own the MPQ2000, how to use it to do power quality analysis. And, for those of you who are interested, you still you can still read the presentation, and you'd be able to see how we can use the MPQ2000. So the presentation is divided up into these 4 sections. We'll start off with a short introduction to the MPQ2000. We are going to look at the different capabilities of the instrument. We are going to familiarize ourselves with the instrument in the 3rd section, and eventually in the 4th section, we're going to see how do we use the MPQ2000 to do a power quality analysis or a power quality study. So let's get into the 1st section. So this is the MPQ2000. It's our 3-phase power quality analyzer. It has 4 different voltage channels. Each of the...
I just gave my...
Andy, can you mute yourself? The MPQ2000 is a 3-phase power quality analyzer. It has 4 voltage channels. Each of the channels is rated for 1000 volts and is capable of measuring AC and DC voltage. It has 5 current channels, and with the CTs that we provide as accessories, each of those channels can be used to measure a maximum of 6000 amps. The data analysis can be done on Megger PQ, which is the free software that we provide. There's no license required for it. You can, even if you don't own the unit, you can register on the Megger website and get access to the software. If you're interested in the MPQ2000, you're free to just register on the website and download the setup file, install the software, and take a look at it. So these are some of the features of the MPQ2000. One feature is that it's powered off of the VA channel. Right? So the voltage channels are provided at the bottom of the unit, and whatever voltage appears on the VA channel is used to power the recorder. This is important because when you set the MPQ2000 at a location, or any recorder at a location, you'd be recording for weeks or months, depending on what exactly you're looking for, like Andy mentioned earlier. So it's important that the recorder be able to power itself and doesn't need to rely on, let's say, a power outlet as an external source of power. It has an IP54 weatherproof enclosure, so that makes the unit really rugged, and it can be set in locations which are outdoors and can still work in extreme weather conditions. There are different. There is a configuration verification feature on the MPQ2000. So before you start the recording, the unit conducts some preliminary checks on the before you actually start the recording, and lets you know that if there's something wrong with the configuration. So let's say you program the recorder to record on a Y connected system, and you hooked up the recorder on a Delta connected system, then you will get an error message saying that there's something wrong here, and you need to check your connections. If you connect your CT backwards, you're going to get a warning message. So all these different checks are done by the unit, and that kind of minimizes operator error. Right? If you set the recorder on a location, record for a week, and then download the data and realize that you did something wrong while setting up the recorder, and that's a complete waste of your time and effort, right? So we want to avoid that, and that's the reason we have provided this configuration verification feature on the unit. Besides that, there is automatic CT identification. We provide different types of CTs as accessories. We provide rope CTs. We provide split core clamps, a clamp which is capable of measuring DC as well as AC. And these CTs have different ratios on it. And the unit identifies the CT ratio when you directly connect the CT. The CTs are powered by the unit, so they do not rely on a battery. There's an IC standard called 61000-4-30, which is the standard for power quality measurement techniques. And that standard mentions 3 types of instruments: Class A, Class B, Class S. Class A have the most stringent requirements, and the MPQ2000 is a Class A compliant instrument. It also has onboard data analysis. So we are going to look into this in the future slides, but the graphic user interface on the unit, on the graphic user interface, you can do a lot of things. And one of those is onboard data analysis, which Andy touched upon in his part of the presentation, and we are going to talk a little bit more about that towards the end. Memory-wise, the results are stored on the SD card, and the default SD card that we provide has a capacity of 8 gigabytes, which is more than enough. I recorded at my home actually just last week, and the size of the file was 3 megabytes. And so if you record, if you have a limit of 8 gigabytes, you can see that, I mean, you can record for a really long duration without having to worry about running out of memory. But still, if you want to expand the memory capacity, you can always get another SD card off the shelf, and you can go all the way up to 32 gigabytes on that. There is an approved list of SD cards that we have on the Megger website. So if you're not sure which model to get of the store, you can always check the list on the Megger website. For backup, there is a nickel metal hydride battery inside the unit, which has a discharge time of up to 6 to 8 hours. So if everything is good, if there's voltage on the VA channel, the recorder doesn't need any external source of power. But let's say if an outage occurs, the voltage goes missing, then in that case, the battery kicks in and the recorder can still continue for up to 6 to 8 hours. Now let's get into the second section of the presentation where we are going to look at what the MPQ2000 is capable of measuring or detecting. So these are all the parameters and events or power quality phenomena which can be detected by the MPQ2000. Let's go over these slides real quick because Andy has talked about the theory and kind of explained each of these topics a little bit. So let's just run through this section real comparatively quickly. So let's talk about what the MPQ can measure. It can measure voltage, current. I already covered this. And it can measure harmonics up to 50th order, and that's a requirement as per the IEC 61000-4-30. And the measurement is done as per the standard that's shown there. On the software, you can analyze each cycle on any of the waveform captures and get up to 128th order harmonics. Harmonic indices can be determined, so total harmonic distortion for voltage and total demand distortion, which is the preferred index for current current harmonic measurement. And you can look at demand parameters. You can look at the different power factors, true power factor and displacement power factor. You can look at the energy consumed. You can look at the IEC unbalance. So the IEC unbalance is the preferred form of measuring the unbalance because it doesn't just look at the magnitude, it also looks at the phase angle. Right? And these are the formulae that are used to get the negative sequence factor and the zero sequence factor. Then short duration variations, which are sags and swells, and the typical limits are set at plus minus 10% of the nominal voltage. Here you have a waveform capture for a sag, which is a decrease in the RMS value of the voltage. So here you can see that for about 4 cycles, the magnitude has dropped. You can detect transients. Transients with durations greater than 64 microseconds are detected through a feature called subcycle event capture. The waveform capture that you see there is an example of one such event. And then you have shorter duration events called electrical fast transients, which can be detected using a different circuit, using a separate circuit, which utilizes a sampling rate of 1 million samples per second. So it's a much higher sampling rate, and it helps the MPQ2000 detect EFTs or VFTs, very fast transients. Other power quality phenomena include phase deviation events, where the phase angles deviate from the nominal angles, mains signaling, where it's detection of high frequency signals sent over power line carriers, rapid voltage change events, which are kind of similar to sags and swells, where there's a change in the RMS voltage. Flicker events, flicker values are measured as per the IEC 61000-4-15 or IEEE 1453, which basically derives from the IEC standard. And you can get short-term, long-term flicker values of the terms that Andy covered in his part. So let's get into the next section where we get to know the instrument, right? So we talked about power quality, and Andy covered the theory bit. Let's get into the instrument now in this part of the presentation. So how does the MPQ2000 function? The basic signals which it relies on is voltage and current, right? So here is it's kind of a relationship between the different parameters. So voltage and current are what are measured, and from that it derives all these other parameters. So let's take one waveform capture from the MPQ2000 and kind of zoom into a small section of the waveform capture. We can kind of break this up into different data points, and each data point is captured every 64 microseconds, and that's because the sampling rate is 256 samples per cycle. So we are basically measuring 256 instantaneous values every cycle, and the RMS value is calculated every cycle. The IEC 61000-4-30 gives the requirements, and one of the requirements is for the RMS measurement interval, which is 200 milliseconds. So that's supposed to be the measurement interval for RMS value measurement. So all of these values that are calculated over every cycle, they need to be aggregated to give you a 12 cycle measurement value, and that's the requirement as per the standards. for sag swell evaluation to detect when a sag or a swell starts and when a sag or a swell ends. The RMS value that's considered for that is RMS over one cycle updated every half cycle. Now, what does that mean? It means that for event detection, like sags and swell detection, what it looks at is the RMS over one cycle, which would be this particular cycle, updated every half cycle. So as it moves forward by one half cycle, it again looks at the RMS value measured over the cycle that's there. Okay. So this is the layout of the instrument. This is what it looks like. It has a little screen there, and let's go over the different keys there. The screen is not touch screen, and the reason why it's not touch screen is because typically the people who use this out on the field would be wearing gloves for protection, so it's very difficult to use a touchscreen interface with those gloves on. That's why we haven't provided a touchscreen here, and we have provided hard keys so that you do not accidentally press the wrong button. So if you press a button intentionally, only then will that option get selected. So let's go over each of these keys. So first we have the home key, which takes you to the home screen. Home screen is the screen that comes up when you first power on the unit, and we're going to take a look at that in the next slide. About key gives you information on the instrument. So information like the serial number, the calibration date, the firmware version, all of that is displayed when you hit that key. The record key is used to start the recording. There's a switch here which has two positions. There's aux and there's VA. In the aux position, the battery relies on an external source of power. So you would need to connect the power cord to the recorder and connect it to a power outlet. Typically, when you take this unit out in the field, you leave the position on the you leave the switch on the VA position, which means that it's going to rely on the voltage that's being applied on the VA that's coming in on the VA channel. Here's the communication and memory section. So here you see ports for Ethernet connection, for USB Type B connection. You see a USB Type A port for USB sticks, and you also see an SD card slot. So the SD card, as I told you earlier, all the test data is stored on the SD card. The internal memory of the unit is only meant for setup files. There are two yellow shortcut keys there. So there are two modes in which information can be weaved. There's the DMM mode in which you can look at numbers, and there's the scope mode in which you can look at waveforms. Okay. The green key is to power on the unit. The key of the bar graphs is the analyze button. So here, if you hit that button, you can analyze the data statistically with the help of the templates that are there on the inside the unit. The back key takes you to the previous screen. You have navigation keys to move between different screens, different options. You have the return key or the enter key to select any option. So that was the layout of the instrument. Now let's take a look at the graphic user interface. Let's go over each of these options. I'm not going to take you through each and every screen. This is not a full-fledged training, so we're going to keep things brief here. Let's look at what each of these options are. And weave data is the first option. And now here you can weave the data that's stored on the instrument. By default, the file names that are assigned are test followed by the number. Now, if you want to rename those files, and you will see on the screen that there is a rename option over here. On each and every screen, you will see prompts, little prompts at the bottom, and you can follow those prompts if you want to play around with the unit. So here it's basically asking you to press the scope mode key, scope mode shortcut key to rename the file. When would you use it? Let's say you have to record on multiple locations before you can download the data onto your software. In that case, to be able to differentiate between files, you can rename the files on the unit itself. Analyze key is to run a statistical analysis on the PQ data that you have recorded. SD card will show you SD card related information, so you can see the files that are there on the SD card. You can import or export setup files to or from the SD card. You can export the test data to a USB stick, right? So the test data is recorded on the SD card. Now, if you want to transfer data from the recorder to your laptop, one method of doing it is by using a USB stick. So you would use that if you want to keep the recorder on site and you do not want to take it out, but you still want to get the data that has been recorded so far. So in that case, you would just plug in a USB stick and get the data out. Clear the test data, format SD card. So if you get an SD card off the shelf, then for you to be able to use it with the MPQ2000, the very first time you insert the SD card, you will need to go to the format SD card option and format it so that it is usable with the MPQ2000. The DVM mode option is the same as the yellow shortcut key that we saw earlier for the DMM mode. So DMM, DVM, basically the same thing. DVM mode or DMM mode has different screens, and here you're looking at the screen that shows you the voltage, the THD, and the current. You can switch over to different screens. That includes the setup screen where you can alter setup parameters. It's possible to do that now. It wasn't there earlier. We're going to get into that later on. But there is a screen now under the DMM mode for just for setting up the recorder. And the other tabs include power screens, harmonic screen, flicker screen, unbalance. So you can go through all of those screens if you have the unit. The scope mode screen shows you the waveform, the live waveform. So you can hook it up to the system and look at the live data. And then if you want to freeze the screen, you can do that. And then you can look at instantaneous values by bringing up a scan line. You can zoom into a section of the waveform. You can stretch it out, do all sorts of things. And then if you want to look at other screens, there is a screen that shows you the vector diagram. So you can see the vectors for voltages and currents. You can see the harmonic spectrum, the harmonic graphs, as well as interharmonic graphs. The setup option, in the setup option, you can set the date and time, which is very important. You need to make sure that the date and time is set properly on the recorder. This is a very important point, and we're going to touch upon this later on as well. Select is to select a setup file. The unit has default setup files in it, and also you can create custom setup files and save it on the recorder. You can delete setup files, and under preferences, you can select the colors of the traces that appear in the scope mode. You can increase the thickness of the lines. You can enable the recorder to shut down if it's been inactive for a certain amount of time. And then if you go into the USB option, all these options that you see are pretty similar to the SD card option. The help option brings up information on the instrument. It'll show you the serial number and all of that, and it has a shortcut key. The key with the question mark that we saw earlier is the same as the help option. Now let's look at the software layouts. The way the software is laid out, it's pretty similar to the software that we had for the predecessor of the MPQ2000, which was the PA9 Plus. So people who use the PA9 Plus would kind of find this software a little familiar. So the way the icons are laid out, and before we get into the icons, let me just show you this. When you install the software, make sure that you select the MPQ2000 here, and over here you have a tab which shows you, or there are 3 tabs over here. It says Data, Default, Custom. Data is where all the data files appear. Default is where the default setup files appear, and Custom is where the custom setup files appear. Now let's go over each of these icons. So you have these icons which you would be using mostly, and these icons have been laid out in the order in which you'd be using them. So first you'd be creating the setup file, right? Once you've created the setup file, you would program the recorder with it. And then you would install the recorder on location, the recorder would record, and after the recording is complete, you would download the data. Now, if you want to connect the instrument to your laptop, you can do so, and then you can click on verify connection to verify that it's communicating. You can bring up the remote screen where it shows you some things like the live information. You can start the recording remotely. You can look at the serial number, the hardware version, and all of that. These options are related to data analysis, right? So once you've downloaded the data, you want to analyze the data, you can do so by creating reports. You can create charts. You can do a statistical analysis. If you want to export the data, some of the parameters to an Excel format, you can do so by using the export to Excel option. Now let's get into the final section of the presentation, which is steps in how to use the MPQ2000, right? So these are the steps, and you would start off by creating a setup file. Then you would program the recorder. you would install the MPQ2000 on location. The recorder would record, and once the recording is complete, you would download the data from the unit, and then you would analyze the data on the Megger PQ software. And we are going to briefly go over each of these steps. This is what this is the first step, where you need to create a setup file on the software. Right. So how do you create a setup file? Excuse me. What you do is you click on create setup file, and it brings up the basic screen. This is the basic PQ setup, as it says here. You make some basic selections, and you can select the type of test here. And what that does is it tweaks certain settings in the advanced section automatically without you having to get into the advanced section. So you have two ways. Either you can just make the basic selections here, hit save, and that's it. The job is done. You just need to program the recorder with it. Or if you want to be thorough, if you want to go over each and every parameter that's there in the setup file, you can go into the advanced section and you can look at all those things. Now, a third option that you have now is just, there's a bunch of default setup files which are provided on the unit as well as on the software. You can alter those setup parameters on the unit itself and program the recorder on the unit without having to create a setup file here. So we have tried to make things easier for you on that front by providing these options. There is a lot of setup files provided by default, and you have the option of altering the settings on the recorder itself. So you do not have to rely on this, but I'm going to go over this anyway, so that if some of you are interested in actually going through the whole process, you can just follow these steps. So this is the basic screen, and you have the option of saving the setup file after making the changes here, or go into the advanced section by clicking on this. Once you click on the advanced option, this screen appears, and here the way you need to go about it is basically go over these 4 steps: RMS, waveform, general, scheduled run, and go over this table. I'm going to talk about what each of these points concern. So the RMS, when the RMS point is selected here, you will be able to select the demand interval. You'll be able to select the RMS interval. You can set the limits for sags and swells. Okay. Under waveform, you'll be able to select the capture rate for time-based waveforms. You can select the number of cycles, enter the number of cycles for event-based captures. So there are 2 types of waveform captures. Time-based is where it captures waveforms based on the time interval that you put in there. So every hour, every 6 hours, if you want waveforms, you can do that. And as Andy mentioned earlier, it helps you get baseline measurement data. Now, if you want to capture event-based waveforms, then you can select the. Of course, it will capture waveforms every time there's an event. You do not need to check or uncheck that option, but you can select the number of cycles here. And the limit for the number of post-trigger cycles on event-based captures is 600 cycles. So that's a lot of cycles. And timed waveform capture has a limit of 200 cycles. So a lot of cycles can be captured, and of course, memory-wise, you're good as well. So if you run into an application where you need to capture a lot of cycles, you can freely do that. Thd intervals can be set here. Under general, the default frequency is set to 60 Hertz. You can enable or disable. You have the checkbox for frequency recording, flicker recording. There's a clock hour orientation option here, which enables you to kind of sync multiple data files by having the time data stamps adjusted according to the recording interval. Checkbox for main signaling. Scheduled run, you can enable the recorder to start the recording at a scheduled date and time. You can even select the length of the recording. So just those 4 points, and then you go over this table where limits have been selected, ratios can be selected, and basically there are limits and ratios. That's all there is to it for different types of events. So that's what it is. It's basically 5 points, 4 of those program criteria, and eventually this table, and then you're good. You can save the setup file once you're done with this, and then program the recorder with it. But as I said earlier, this is the most thorough option that you have if you if you want to go over, if you want to be familiar with each and every point, be thorough with the way you're setting up the file, then you can go through this option. Otherwise, the easier options are always available where everything is kind of taken care of. And if you want to tweak, make some minor changes, you can do that on the recorder. Communicating with the recorder, so you can communicate your you can establish communication between the unit and the laptop, and the way of doing that on the software is either by an Ethernet cable or through a USB cable. Here I use the USB cable, and if you look at this on the top right, you will see a box which says COM16. So basically, when I connected the recorder to my laptop, it automatically detected the port number that was assigned to it, and then I can verify whether it's communicating with the unit by clicking on Verify Connection. And if the communication established is good, then I would be able to see the firmware version on the unit. Now, if I want to bring up the remote screen, then I can do that. Typically, you won't be using this, but just letting you, just showing you what it would look like. Now here you can, as you can see, you can start the recording, you can weave information on the instrument, you can see the date and time, and as well as set the date and time on the recorder. You can clear the data from the recorder, you can see how much memory remains, what's the status on the battery, things like that. Okay, so that's how you communicate with the instrument. It's pretty straightforward. You do not need to make any changes. It automatically detects the unit. Programming the recorder. So there are two ways in which you can program the recorder, either directly by actually connecting the recorder to your laptop. So you follow the step that we covered in the previous slide. You connect your recorder to the laptop, and then to program the recorder, you will either go with Analyzer and Load Setup, or click on Install Setup File, which is the main option that's provided. Both of them are basically the same thing. Okay. If you click on Install Setup File, you get this prompt where it asks you if you want to install default setup files or custom setup files. There are a bunch of default setup files provided that you can see on the left there. And if you create a setup file on your own, that file will appear under the Custom tab. So now I'm going to click on Custom here, and that takes me to the folder where the custom setup files are stored. I can pick one of these files, the extension is PQ2S, and then I click on Open. When I click on Open, the software starts programming the recorder, and at the end of the process, I get the message, it says Analyzer successfully programmed. Option B is to transfer the setup file from your PC to the MPQ2000. So you can do this using either the SD card or a USB stick. The way to do that is by going to File and then selecting Export Setup File. So you go to File and then select Export Setup File, and when you click on that, it opens up a window where the to location is automatically set to the removable drive. It could be the SD card or the USB stick, and the from location is set to the custom setup folder, which is where the setup files are stored. So you click on Browse, and that opens up the custom setup folder, and there you can select the setup file that you want to program the recorder with. And then you click on OK, and it does the same thing. It converts the file into a binary format, and it's stored in the SD card or the USB stick. And then you can take that SD card or USB stick, insert it into the recorder, and then download the setup file from the USB stick or the SD card into the recorder. So that's one additional step that you need to go through if you do not program the recorder directly. Okay, so you need to download the setup file from the SD card into your recorder and then activate that setup file. Installing the MPQ2000, let's just go over these pointers, and Andy kind of covered some of these in his section. It's very important to get information on the asset prior to recording. So even before you go out there, just make sure that you have information. If you're recording on a transformer, make sure you know what the nameplate information is. The voltage rating, I mean, that would typically be clear, but you also need to find out what the rated current is, so that you can set the CT ratios accordingly, take the right CTs. Where the necessary PPE, gloves are important because you're working at high voltage levels, 480 volts, 600 volts. Make sure that you're wearing PPE there. You can wear safety glasses too. Make sure that you're not that you have sufficient insulation on your shoes, on your footwear. You're not standing, wearing light footwear and standing on wet ground. Avoid all of that. Make sure that safety is very important when it comes to this, especially because you're working with live voltage here. Connect the ground of the unit to the ground of the system. That helps you measure, get reliable results. So make sure that the ground is connected there. Go to the unbalanced screen. So we have the unbalanced screen, and I told you earlier that the unit runs multiple preliminary checks, and it lets you know if it sees something wrong. But if you do not want to completely rely on the unit, if you want to do some checks by yourself, you're welcome to go to the unbalanced screen, and here you can look at the vector information on the voltage and the current. And typically the loads are inductive in nature, so you will see the current vectors placed clockwise, placed at an angle clockwise with respect to the voltage angles. You'd be able to see what the phase rotation is. So it gives you a lot of information. So I would recommend going to the unbalanced screen, taking a look at it just so you can yourself verify that you have done the connections the right way. Check the date and time on the MPQ2000. Make sure that it's set to the current date and time. That is very important, because if you want to correlate an event with what happened outside of the asset, then it's very important that that the event date and time be accurate. Okay. Simple things like make sure that the recorder is recording before you leave. Once you hit the record button, it switches over to the recording screen. It says recording on top. So when you see that recording screen, then you know that the recording has started, and now you're good to go. Once the MPQ2000 has recorded the data, you can get the data off of the unit and transfer it into your laptop. There are two ways of doing it. Either do it directly by connecting your unit to your laptop. So this is option A, where you are downloading data directly from the recorder to your laptop. You can do that by clicking on Analyzer and then selecting Retrieve, or you can click on Download Data, which is the third step that's provided over there. When you click on that, the software attempts to communicate with the unit, and this window opens up, and you would be able to see the test files that are there on the unit. They would populate in that window over there. And those, as you can see, are default file names. If you had renamed those in the unit, then you would be able to see the names of those files. And you can, if you want to download one individual file, you can just click on test name to uncheck all the options, and then select the test file that you want to download. And then you can also rename it, just as you can rename any file on your computer. Just click on it once, and you will be able to rename it. There are additional fields provided for the location on which the recording was done. You have two additional fields to add comments if you want. When you click on Retrieve, it starts downloading the data, and once the download process is complete, it says data retrieved and converted successfully. You can click on OK, and to see if the data has been downloaded, you can click on Data on the left, and you'll be able to see the file under Data. Now let's look at option B. Option B is to transfer the data from the recorder to the laptop using an SD card or a USB stick. Now here, what we do is we click on File, and then click on Import. And then depending on what we are using, we select the right option there. And it brings up a window where I can see what the files, what data files are stored in that removable drive. Again, if I want to download an individual file, instead of downloading all the files, I can just click on test name, and that unchecks all the options. I can then select the file that I want to download, rename it if I want to, and then click on OK. The file gets downloaded, and at the end of the process, the file would appear under the Data tab. Now, let's get to the last part, which is analyzing data using the Megger PQ software. So how do you go about it? There are basically 3 or 4 ways in which you can look at the data. One way is by looking at reports. You can create reports for different parameters. You can click on create report, select a file first so that that option becomes available, and then click on create report, select any of the report types, and then click on create. And that way you are able to generate the report of your choice. Now there are different report types. We have a time constraint here. I'm not going to go over each and every report type, but you can kind of go over the topics or the types that you see there, and you get an idea of the data that you would see inside that report. These reports can be saved as text files, and from the text file you can copy it over to a spreadsheet if you want. And yeah, it's basically lots and lots of numbers. You can create charts, and these are the different chart types that you can create. So you select the chart type, and when you click on create, that creates a chart. Now in the lower half of the screen, you can see there are some selections here. You can choose which parameter you want to see on the chart. You can the axis is auto scaled, but if you want to manually scale, manually decide the scale, and then you can do so by typing in the numbers here and checking these boxes. You can assign different colors to the traces. There are 2 line types to choose from, solid or dashed. You can assign a title there. You can choose how much of the data you want to see here. So all those things can be done. And again, if you have the software, you can go over each of these different chart types. Now, the third way in which you can analyze data is by looking at the waveforms, right? And there are 2 types of waveform captures that the MPQ2000 does. And it's not either or. It does both types of waveform capture. So it can do both at the same time, which not many, I don't know how many other recorders in the market can do that. So if you want to look at event-based waveform captures, any event-based waveform capture that has been done, this is this kind of screen that pops up when you click on that option. Now here you can see the different types of events which have been captured. You can filter different types of events. You can choose which traces you want to see on the waveform capture. You can zoom in, this kind of zoomed in. And here you can see the date and time at which the event was captured. You can bring up a scan line, and so that you can see instantaneous values on the waveform. So this is what the event waveform analysis screen looks like. Now here you can see an option to export a ComTrade file, which has been added recently. So if you want to export any data in the form of ComTrade in a ComTrade file format so that it can be used by any protection equipment, that can be done. You can do a detailed harmonic analysis on any of the waveform captures. It doesn't matter if it's event-based or time-based. You can go into this option and then select any cycle, any particular cycle in any waveform capture, and then analyze the harmonics on it. And you can go all the way up to 1/28th order on that analysis screen. Now the time waveform analysis screen looks like this. Now here you can select which parameters you want to see. You can choose 4 different harmonic orders, and you can see the harmonic charts for them throughout the recording. So you can see how the harmonic levels changed for any parameters. Over here, we are looking at the A phase current, and we are looking at the 5th, 7th, 11th, and 13th harmonic. So you can see how the values, where the values were throughout the duration of the recording, which possibly lasted for close to a week. And you can again do a detailed harmonic analysis for time-based waveform captures. You can look at the harmonic spectrum for the first cycle of the waveform capture. This is the waveform capture itself, and you can see the values here. So this is basically what the timed waveform analysis screen looks like. Now the scan line here represents this particular waveform capture. Many other waveform captures were done. You can see that the scan line position here is 93, which means this is the 93rd time-based waveform capture done during the recording. So you can move to different waveform captures by moving the scan line. Let's look at statistical analysis. So this is what the statistical analysis looks like. So the analyze button that you see here, if you click on that, this is the screen that you get. Now here you can, basically the way in which this is done is you analyze the data statistically. So you have all of these data points that you have gathered, and it's recommended to record for at least a week to be able to analyze the data in this manner to get a fair analysis. So you measure different parameters, right? You measure the voltage, frequency, you can measure unbalance, flicker, THD, and all of those parameters have been assigned limits. And there are two types of limits. There's narrow limit, there's wide limit. And so you have narrow band data and you have wide band data. Narrow band data can be called the majority of the data, and wide band data can be called the complete data, which is why wide limit is set at 100%, narrow limit is set at 95%. So with this, what it means is that the narrow band data would be the data that's recorded over 95% of the week, or the 95th percentile of the data that's being recorded. This applies to different parameters, except frequency. For frequency, it's 99.5, but for all the other parameters, it is 95%. So there are predefined templates provided on the software. There are two templates you can choose from, or you can create your own and save it, program it on the recorder as well. Now, if you hit analyze with a certain template, if you try to analyze a certain data, you get a screen like this. So in this screen, basically you get a single snapshot of the entire data recorded for a week, and then you can figure out where it's bad and which parameters are okay. So here you have these different parameters, and what's looking at is where does that data stand with respect to the limit. So the green limit represents the narrow band limit. And if there's a legend right here which says that green is the narrow band limit, the brown line is the wide band limit, the blue section of the graph is the narrow band value, and the brown section of the graph is the wide band value. So the narrow band value is the majority of the data, and you want that data to be under the green line, which is the limit for the majority of the data. And then you have wide band value, which is the complete data, and that data needs to be under the wide band limit, which is the limit for the complete data. So if the brown section of the graph exceeds the brown line, then it's a fail. If the blue section of the graph exceeds the green section, then it's a fail. For the data to have passed, for the recording to be a pass, the blue section needs to be under the green line, and the brown section needs to be under the brown line. So it kind of gives you a snapshot of the, if you are doing power quality evaluation at a site, then this is a good way to look at the data, look at the overall data. So it gives you a single graph where it shows you whether it's a pass or a fail. So we have made some recent updates to the Mpq2000, and I'm going to go over those so that those of you who have the unit, they are aware of these changes, and they can update the unit and make use of these features. There's an onboard setup, as I mentioned earlier. It's possible to now make setup changes on the recorder itself. It wasn't possible to do that earlier. So if you go on the DMM mode and select the setup tab, you'll be taken to this screen where you can enable and disable channels. You can set ratios. You can select the intervals by going on the interval tab. You can modify the default files, create your own. You can save the file that you've created on the recorder without having to rely on the software. The limit on the number of cycles on event-based waveform capture has been increased to 600 cycles. It used to be 99 cycles earlier. Now it's been increased all the way up to 600 cycles. So let's say if you want to record 10 seconds worth of data continuously, you can now do that using this feature. The file size is limited to 100 megabytes, but the memory depends on the capacity of the SD card. So the way this works is if you are recording for a really long time, and again, the recorded data has to be a lot for the file size to reach 100 megabytes. Typically, the file size would be, as I said earlier, I recorded last week and it was just 3 megabytes. Depending on how many waveform captures you have, it might be, let's say, 30 to 40 megabytes for a week-long recording. For it to be 100 megabyte, it has to be a lot of data, and if it gets to that level, what will happen is that a new file will be created. The MPQ will still continue recording. It won't stop recording. It's just that a separate data file will be created. But then at the end, you can merge those data files on the software to make it into a single file. So you have this option available now to merge different files together on the software. There's a CT prompt in the preferences. Now the CT prompt, if it's enabled, then you get a warning if you try to use a CT with the MPQ and the CT ratio on the CT doesn't match with the CT ratio programmed on the recorder, then it will give you a warning saying that there is a mismatch and you need to take action. That will happen if the CT prompt is enabled. If it's disabled, then the recorder automatically adjusts the CT ratio on the setup file to match with the CT that you have connected. The demand interval is separate from the RMS interval, and it goes all the way down to 1 cycle. So the RMS interval is set as per the IC standard, which says that you need to come up with 12 cycle measurement intervals, right? So the data is aggregated to 12 cycle intervals. But if you want to look at cycle by cycle data, you can do that by using the demand interval. The updates can be accessed on the Megger website. You just need to register there and then search for MPQ2000, go into software, and you'll be able to access the firmware update and the latest version of the software. And the firmware version is 1.407. So if you do not have firmware version 1.407 on your units, please go to the Megger website and get the update to make use of all these features. So that was my presentation. Thanks a lot, and we can open for questions now.
All right, thanks a lot, Venkat. So at this time, the presentation portion of our webinar has officially concluded. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's a field where you can also request a quote or demo on any Megger products. A copy of these presentations, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars as well as register for upcoming webinars on our website at us.megger.com/webinars and register for our state-of-the-art diagnostic technologies for proactive cable condition assessment on Friday, October 23rd. All right, let's jump into the Q&A session. Our first question I'm going to be directing to Mr. Andrew Sagal. Andy, we get a lot of DC bus over voltage even when equipment is not running. Filter seems to help, but we still get them when the filter is on. Where would you look at for power quality issues? The transformer is already tapped down a little, but it hasn't helped. I think we might have an audio issue over on Andrew. Here, Andrew, let's try that.
Oh,
there we go.
Okay.
Yeah.
It's tough to say I'm on mute when I can't say I'm on mute. But this right here, when you're seeing a DC overvoltage, one thing to keep in mind is that the DC bus is going to be generated from AC rectifiers. Okay, so the first thing to look at is that, when you have depending on the design of the AC rectifier, the voltage you get on that bus is going to be about 35% higher. Like if you have a 3-phase rectifier, that voltage will be about 35% higher than the RMS voltage of the that's coming into the rectifier. So you'll automatically see that. But I see in the question that you've also tapped down, and that really hasn't helped the problem. So that would indicate that this problem can either be from a faulty rectifier somewhere else in the system, but you also say with the loads off, you're not seeing it. So this really seems to indicate that this is really a harmonic issue. That's most likely the cause of it. So that even in here, it's mentioned that if you are using a filter, it does help somewhat. So, I mean, you may want to try putting a line rectifier in there to see if you can block some of the harmonics. But the ideal thing that I would recommend actually is hooking up an analyzer there and actually taking a recording of the harmonics. Look at both the input to the rectifier and the output of that rectifier to get an idea of what level those harmonics are at and what frequencies they're at, so we can get the proper filtering on them. Of course, that does seem to be the most likely cause of the problem.
All right, thanks very much. Our next question I'm going to be sending over to Dinesh Chajer. Dinesh, does the MPQ2000 have interconnection with Powerdb?
That's a good question. You saw Sanket's presentation. The MPQ2000 has its own software, which is called as MPQ, obviously. The idea behind that is that whenever you're doing power quality study or investigation, you need to look at a lot of data, analyze the data, zoom in, create different charts and everything. And that's the reason why we need a dedicated software for that. So at this point of time, we don't have any interconnection with Powerdb. However, once you are done with the analysis and you create a report, you can generate a PDF copy of that report and attach that to your Powerdb Pro database and create a tree structure where you can have those recordings or the report attached in your Powerdb database. So the recommended way would be to analyze the data in MPQ software, look at the different trigger levels, look at the parameters that is causing a certain PQ event. And once you analyze the data, you create a report, and that report can go into Powerdb in PDF format.
All right, thank you, Dinesh. Next is back over to Andy. Andy, do you consider it a good practice to pass the light to DC to forget the flicker?
Okay. I pretty much think that what this question is really asking is it a good practice to go and use a DC lighting system such as an LED system? And really there's pros and cons to pretty much everything in the world. But when we go to a LED lighting system, which is run off DC, yeah, it's going to be a lot less prone to flicker and RVC, rapid voltage change, depending on the design of the rectifier in it. So in general, they're going to have be less prone to that, so you should see less flickering. And they do have a longer life, and they do use a lot less energy. Now, on the con side, now, since they do operate off DC, that means they have to have an AC to DC rectifier in them. So they do create harmonics. Now, we're talking very low current here, so it's very minimal harmonics, but if you're replacing an entire facility with them, it is recommended to do a harmonic analysis before and after, because to see what impact it may have on other systems. And the other thing to keep in mind, if you're going to LEDs, is that you will need special dimmers with them. So if you're going to be using dimmers, they have to be specially designed for that LED that you're using, so it operates properly with the power supply that drives the LED. And the other thing to note about LED lighting, which a lot of people sort of don't discuss, is the fact that when you're dealing with other lighting systems, you're dealing with a full light spectrum. So you have all different frequencies in there. When you deal with an LED lighting system, you're dealing with a system that is a single frequency. So this has a couple impacts. One, it means that if you purchase an LED light, for example, let's just pick arbitrarily 40 watt, and you pick a 40 watt incandescent, the light that you measure out of the LED will be, the lumens will be the same. But the problem is that even if they have matched lumens, your perception of the LED will appear much brighter to you because it is a single frequency. Okay, and also throwing it out. So you probably want to go a little lower on the wattage of the LED if you're switching over. And the only other thing I'm going to throw out there is that there really have been very limited studies on the effects of single frequency light on the human eye. That really hasn't been done. I've heard of one out of France that was specific to blue light, which they said had some caused some retinal issues, but this is just one study. So again, things we'll learn as we go along with the new technologies.
All right, thanks, Andy. Moving next to Dinesh. Dinesh, are there standards for power quality?
Um, uh, that's a very good question, because we run into this question all the time. And there are a number of IEEE and IEC standards that you can look at or review to kind of get a good power quality investigation done. I will mention some of the standards. So there is a IEEE 519 standard that talks about the harmonic control, and it gives you the limit for the individual harmonic as well as the THD. Then we have IEEE 1159, which provides the recommended practices for monitoring electrical power quality. So if you want to record your measurements, then you need to look at this standard. Then we also have a IEEE standard 1459, which gives you standard definitions for the measurement of different power quality terms under sinusoidal condition, non-sinusoidal, balanced or unbalanced condition, and that standard is IEEE 1459. Then if we move to IEC world, there is a standard which Sanket also mentioned in his presentation. It's IEC 61000-4-30, and that tells you how your recorder should measure different power quality terms. And based upon that, you can define whether your instrument is Class A or Class B type instrument. So that's IEC 61000-4-30. Then there are some other standards like 61004-7, which talks about how to measure harmonics and interharmonics. There is a 61004-15 that talks about how to measure flicker events. And one other I would mention is 61004-27, which talks about how to measure the imbalance in any given circuit. So there are a number of IEEE and IEC standards out there, and I just mentioned maybe 6 or 7 of those. But I highly recommend anyone who wants to do a PQ study, they should look at these IEEE and IEC standards.
Thank you, Dinesh. Next over to Andy. Andy, could you please comment on the difference between unbalance and imbalance, or are they basically the same term?
They're really basically the same thing. Early on in IEEE standards, it was always referred to as imbalance, and in Europe, the IEC standards refer to it as unbalance. And basically, in later times, as you look at the IEEE standards, they're adopting the terminology of unbalanced. But in general, they're just the same thing, different terminology.
All right. And while I have you, the next question will be sent over to you as well. Regarding to CEGRE documents, harmonic measurement is questionable at high voltage and above. How can we solve that issue?
The real problem you're running into is bandwidth here, is in your measurement devices. You're really running into, because now you're dealing with high voltage. You're not connecting directly to it. You're going to be running through PTs and CTs. And this is one of the things I mentioned, is that they are bandwidth limited. So this will limit how high of a harmonic study you can actually do. And now when you're dealing with these high voltage transmission systems, you have new DER systems that are going in that produce higher frequency harmonics, such as solar and wind, because they're going to be using inverters with high frequency switches in them. So you are seeing higher frequency harmonics, but again, how are we going to measure them? And really, the things you have to look at is, well, two things really. Is you'd have to acquire, they do make them, they're expensive, high frequency PTs and high frequency CTs that have the bandwidth to actually measure them, but you also going to have to make sure that the equipment you're using to measure them can go up to the frequencies you're looking at. Now, one of the key things you're going to be, there also may end up getting into is what's called supra harmonics. These are harmonics that go up to about 150 kilohertz. And really right now there's no standards on them. They're just beginning, they're just really in their infancy of how they're doing it, and they're even discussing the proper methodologies of how to record them. Because even with this type of thing, you can get induced signals in the line at those frequencies. So there is still a lot of work to be done in this range, but again, the limiting factor is the CTs and PTs and the equipment. So whatever you're trying to do, harmonic monitoring of high voltage, you're going to need to determine how high frequency you want to measure up to, and verify that the PTs and CTs can have the required bandwidth, and the equipment you're using has it as well.
All right. Next is over to Sanket. Sanket, when can files be renamed? During recording, before recording, or only after recording?
So if you are talking about data files, the data files will be created once the recording is complete, and the default name is tests followed by the number, and you can rename those on the recorder by hitting the scope mode shortcut key. The setup files can be renamed at any time. I mean, on the recorder, you will see the same rename option when you go into the setup file screen, and you can rename the setup files over there. So yeah, basically they can be renamed on the recorder.
All right. Next is over to Dinesh. Dinesh, can you review open delta connections for medium voltage connections?
Okay, so yes, you can use MPQ unit to do a study for a open delta connection. In the user's manual, there are multiple different configurations that are available, and open delta configuration is one of those. So you have to make your connections based upon the diagram, and it would specify how many voltmeters and how many ammeters you would need. So the answer is yes, you can review the open delta connections. The second part of the question is for the medium voltage connection. As you know that these power quality studies are typically done on the secondary side of the circuit, and the voltage recording is limited to 1000 volts. And when it comes to current, you use CTs, and that can go as high as up to 6000 amps. So just keep in mind that if you are trying to measure at higher voltage, you would have to connect it to the secondary side of PTs and CTs to make use of the power quality instrument, because they are limited to 1000 volt AC or DC when you're trying to do the PQ study.
All right, thanks, Dinesh. Next over to Sanket. Can the MPQ be time synchronized to other monitoring or control systems?
So there is an option that I mentioned earlier which said clock hour orientation. If you run into this situation, you can use that particular feature where the data timestamps are synchronized with the recording intervals. So let's say if you're recording with 10-minute intervals, and if you want the data points to appear synchronized, then what you can do is you can set the clock hour orientation to on, and let's say you start the recording at 10:03 a.m. What will happen is the MPQ won't start running the test until 10:10 a.m. and then you get your first set of values at 10:20 a.m. So you have then all your RMS data points will be at 10:20, 10:30, 10:40, so on and so forth. So that gives you a certain standard format as far as data timestamps are concerned, and that helps with synchronizing with other systems or with data files from multiple recorders. So let's say if you're recording data in multiple locations, you can compare data files by comparing the data points recorded at the same times.
Also, can I just add to that?
Sure.
Is that you also have the ability, if you are going to be monitoring online remotely, you can also set it up so that the MPQ will automatically time sync to your network. So it can periodically time sync every 10 minutes, every day, whatever you like it to. So that's another method that you can use as a time sync feature.
All right, good deal. And we'll move on to our last question here. Andy, can a power quality study distinguish the power quality issues discussed previously that may require a harmonic filter solution with a periodic surge being introduced in the system that requires surge protection devices?
Absolutely. Whenever you hook up a power quality analyzer, we want to make sure that we record all the necessary data. So typically with our units, when you select one of the default setups that are in there, you're going to be recording everything. So it's really not an issue. You can really just start recording with them. And when you do that, what you'll see is you're going to get all the harmonics. You'll get your interharmonics. You'll get all your swells, sags, transients, rapid voltage changes. Everything occurs. You'll get on there total harmonic distortion, total demand distortion. And when we look at them, now it's coming down to analyzing that data. And it's pretty simple to actually see what problems are causing something, okay? We can see when we have surges that are causing an issue. One of the things you want to do, though, during that power quality study is that if you do have an issue that occurs, if you have a particular symptom that you notice occurs, just jot down the time, the date and time that it happened, so that you can use this as a reference when you're analyzing the data in case it is a periodic surge that's causing the problem, okay? Otherwise, you know, you very well may be having problems due to problems like harmonics, which are continuous issues that are running, you're running into. But in short, yeah, power quality study can really tell you a tremendous amount about what's causing a problem and how to get the solution to it. Especially since we were talking about that first issue with the DC overvoltage bus. And I mean, these are fairly common, especially when you get into your VFDs and everything. Of course, you can have these problems from so many things, like just the backfeed from a motor can cause your overvoltage bus. So there's quite a few different things, and the PQ study can do that. One of the key things, though, is making sure that you perform a long enough study, too. I've seen people go out there and hook up an analyzer literally for 10 minutes and say they didn't find anything. Well, you need to keep it on long enough so that you actually acquire enough data that you can get the analysis, get all the information you need.
All right. So it looks like we are all out of questions. If you think of anything else, please feel free to contact us offline. As a reminder, a copy of these presentations, certificate of attendance, and a link to the video recording of the webinar will be sent to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you all have a great week.